All right. This is a continued conversation about chapter 2. We are looking at chapter 2, which of course has the title of Elements and Atomic Number. Now, keep in mind that this chapter covers atomic theory and structure of atoms, elements and the atomic number, isotopes and atomic weight, the periodic table, some characters of different groups, electronic structure of atoms, electron configurations in the periodic table, and finally, of course, electron dot symbols. Prior to this particular time that I am choosing to lecture, that this is currently being recorded on the 26th of January, 2022. I have already covered the topics of atomic theory and the structure of atoms. And in the structure of atoms, we discussed the subatomic particles that are the building blocks of atoms. We have defined elements again, and we have talked about the atomic number and atomic weight, and we've talked about isotopes. So those topics have already been covered. We've already looked at pretty much everything up to section 2.3. Therefore, this lecture is going to pick up off the continuation of that at section 2.4. And here we'll be looking at the periodic table. So in our discussion of the periodic table, one of the most important things to be able to do is, of course, and the topic I know in the book states this under learning objective, it says locate elements on the periodic table, classify them as metals, nonmetals, or metalloids based on their location. Also, I want you guys to be able to understand what information is being presented to you directly on the periodic table. So you need to be able to locate the element. And of course, one of the things that can help is knowing the layout of the periodic table, and in correlation to that, knowing the type of element you're looking for. Because if you're trying to find something, if you know the layout of that particular general, say like map, and you know what part of the map you should be looking on, then it should be very easy to find. So if we draw a very general layout of the periodic table, and this is a very rough sketch, as you can tell. It looks something very, very vaguely like this. Now, one of the things on the periodic table is metals, metalloids, and nonmetals are located in very specific, general, not specific, but very general ideas. So if you head left on the periodic table, you become more metallic. And in general, if you head to the right, and especially if you head up, you become, let's try this actually in a different color. You can probably guess where I'm going with this based upon the general trend of course, heading left and somewhat down, you become more metallic. So if that's the case, then going to the right and kind of going to the upward direction, you become less metallic. Now, this sketch of the periodic table is rather so poorly done that I will actually redo it, and we'll say that the periodic table looks probably more something like this. Like so, and then there's kind of a larger section like this. And that is a little, just slightly better version of the periodic table. Now, when you look at the periodic table, you will see something that people often refer to as the staircase. It starts here, right next to boron, and kind of staggers its way down the periodic table to the right-hand corner. And this staircase, or this border, as it kind of becomes roughly separates and fairly effectively separates metals from nonmetals. And the elements that run right along it are actually the metalloids. So if you're an element right next to this staircase, so-called, you're a metalloid. And being a metalloid, as the word kind of indicates or suggests, is you're going to have properties of both metal and non-metal. If you're metallic, metals tend to be very different from non-metals. So let's talk briefly about what that means. Metals have very strong tendencies. They tend to be solid at room temperature. Now, of course, mercury is a classic example of something that is definitely not a solid at room temperature. It is a liquid at room temperature. There are a couple of other examples of elements out there that tend to be quite soft and malleable and approach being liquid at room temperature. But mercury is really the best example of something that defies the trend toward being solid at room temperature. They are also lustrous, which is essentially a fancy word for, ooh, shiny object. And your book says, when freshly cut. They are also, in general, excellent conductors of both heat and electricity. And they tend to be brittle and inflexible. They tend to be brittle and inflexible. Oh, no, wait. That's entirely wrong. Let's actually put a line through that. They tend not to be brittle and inflexible. And like anything, these lectures may contain momentary glitches. They tend to be malleable. And I had a 50-50 chance on that one. But think about what we do with metals. We shape them. We utilize them either through heating them up and pouring them into a particular form we want them to take, or we even have people like metal smiths who will heat them up to a little bit and shape them. Think about a steel paper clip. That is foldable. It's bendable. Wires are also foldable, bendable. They don't just snap usually the first time you bend them. So metals tend to be malleable. Like I said on the previous slide, they also tend to be on the left-hand side of the periodic table. There are, according to your book, 94 metals that, or I should say, 94 metals, or another way of putting that is, as the way that your book puts it, is 94 elements on the periodic table classified as metals. In comparison to that, there are only 18 elements classified as nonmetals. Now that is significantly different. And look at that ratio, okay? So when we think of things that we are familiar with, metals are very familiar to us because a lot of elements are metals. Although there is, to quote from your book, although there's some debate as to which elements to include on the metalloid list. So the third group that I mentioned, metals, nonmetals, the metalloids, the ones that are considered to have properties of both metals and nonmetals, the ones that people tend to agree on are boron, silicon, arsenic, germanium. So, germanium, and let's see, germanium and antimony and tellurium. So those are the way that we talk about metals, nonmetals, and the metalloids. Another way to look at the periodic table are to look at what we call the periods. And periods are rows in the periodic table. And of course, if you've forgotten, and that's quite all right if you have, rows run left to right. People often say, oh, horizontal rows versus the groups, which are the columns of the periodic table running up and down, or the vertical columns. And of course, if you need to think about columns, just think about columns of Greek columns, Roman columns, architectural features. The columns are always up and down. That's a very good way to remember them. When we look again at a very vague outline of the periodic table, that would look, there's a bad line stray there. Trying to keep this as simple as possible. The periodic table, again, vaguely like this. And then if we start to kind of gently draw in some actual division into the periodic table, then like so. It's not quite right. It should actually be something like this. And then, of course, that puts us something like this. Now, if you are looking at the periodic table, and you'll actually notice it's not completely accurate. It should actually look, we are going to make it look exactly like the periodic table. It should look something like this. And this will start to look a little bit more like the periodic table that you might be seeing in your book. So there's the columns. We've got 2, 3, 4, 5, 6, and like so. And then this gets divided up a bit more. 2, 3, 4, 5, 6, 7, 8. That should be actually 10 in there. This is a general idea, okay? And so then, of course, that means going this way. If you move left to right, you are traveling in a period of the periodic table. And if you happen to go up and down in this fashion, it doesn't have to be specifically that one. any one of these, and even ones that are not marked, of course. Same goes for the rows. These are the groups. So if you move up and down, then up and down in red would mean that you would be traveling in the same group. Now, there's a reason I did not actually want to draw this like this. What I actually wanted to draw it like was this. So, imagining that that doesn't actually extend down into the area that has a missing gap. But if you move back and forth across this little space or within this little space, you will be moving within the same period. And that is important because there is a difference in how the periods look between this little center section and the other two portions. So moving in these little rows here, you're within the same period. You would not be doing so entering into that middle section. I'll explain that again when we start talking about electron configurations and we start talking about how the periodic table is laid out to help you figure out electron configuration. So in general, that is the situation when it comes to section 2.4. Now I'm going to move on to section 2.5. And my goal with this is to make these lectures accessible to you, but at the same time, I am trying to make sure that they aren't drawn out and long, so you feel like you're slogging through an endless amount of chemistry. So I'm going to try to speak a little bit faster, and I think there are ways to slow down the video when I post it to YouTube. However, now we're talking about 2.5, which is talking about some characteristics of specific groups. Okay, so recall that groups move up and down. They are columns of the periodic table. So the groups of the columns. That's what we are talking about. Okay. Looking at your periodic table, if you are looking at a picture of the periodic table in your book, so here we are. I've taken a moment and inserted a periodic table into this slide. You can see here's the general layout of the periodic table. Remember, from the previous section we talked about, we had staircase that runs right along here, defining the general separation of metals from nonmetals. And of course, the ones that are close to it tend to be the metalloids. But this section now we're talking about the groups. And specific groups actually get called families sometimes. But so this section right here, just this column right here, starting with hydrogen, this is generally labeled group 1. And we shouldn't actually include hydrogen in there because hydrogen itself is actually a nonmetal. So let's actually exclude poor little hydrogen, like so. So excluding hydrogen, this group 1 section right beneath hydrogen, this group 1 are known as the alkali metals. Alkali spelt actually not quite like that. Let's spell this correctly, of course. There we go, alkali metals. These are the alkali metals. They are lithium, sodium, potassium, so on and so forth. They're shiny, they tend to be very soft, as your book indicates, it's got they have generally low melting points. They are alkaline, and alkaline is another way of generally saying that in water they are not just in water, they behave in a basic fashion, and that's not the slang term calling these metals, oh, they are such basic metals. No, we're not doing that. That actually has to do with acids versus bases, which we will come to in a later chapter. I may define that for you guys earlier a little bit more generally, but for now, let's just say that they are basic. That means they tend to, well, have a pH higher than 7, for example. And again, I don't want to spend a lot of time emphasizing things like that when we have so much information to cover, and I don't want to get sidetracked. They are generally very highly reactive, and therefore they are almost never found. You could say essentially that in nature they are never found in just pure form. They are in ionic combinations with other substances, other elements, I should say. Right next to your alkali metals, the next group right there, this is group 2, and group 2 are the alkaline earth metals. Now, the alkaline earth metals include, of course, as you can see in this, beryllium, magnesium, calcium. They are silvery, just like the other ones, but they are less reactive than the alkali metals right next to them. They are also, however, still never found in pure form out in nature, just like the alkali metals. Now, the next group that really is one that tends to be talked about is right here. Starting with fluorine, we drop in this group. So, and this right here is group 7. This is group 7, and these are known as the halogens. Okay. The halogens are group 7, fluorine, chlorine, bromine, iodine. They are, unlike the metals, they are colorful and they are corrosive, quite corrosive. Now, that of course comes to the general assumption that you know what corrosive means. And that is not a fair assumption. It's always good to define things. Corrosive. You may be familiar with the idea of substances that kind of eat away at other substances. You could say, like, quote unquote, salt water is corrosive. It eats away at metal structures, cement structures. What it actually means is that corrosive substance is reactive with the other substance. Corrosion is a chemical reaction that is actually causing a conversion of the two substances from one thing to another. Now, finally, so we've mentioned the halogens, highly corrosive, colorful members of the periodic table. And right next to them, we have, let's see, what would be the appropriate color. Let's go with something like this. These guys, starting with helium, neon, argon, krypton, xenon, and radon. This group right here, this little nestled column right here, these right here that we could call group 8, 2, 3, there's group 8. These are your noble gases. These are the gases of nobility. And what that means is that they are highly non-reactive. The opposite of most of the other elements here is they are highly non-reactive. Okay. Now, if we actually talk about a periodic table that you will probably see in your book, and you'll see other places, they actually kind of start labeling these Group 1A and Group 7A and Group 8A. And technically, you can number all of these Group 1A, Group 2A, so Group 2A, Group 3A, Group 4A, Group 5A. You see there, you can actually see that already having been done on this periodic table that I pasted in. A means the sections of the periodic table that are not a part of the section that is lower than the rest of the periodic table. So what we then will do is kind of go, okay, well, what about the section that we're kind of hinting at being called B? This guy right here, running all the way from there over to here. We could call them essentially 3, 4, 5, 6, 7, 8. And then you've got 1B and 2B, whatever. We can call this the B section, if you like, to start with. What this is this is the area that elements lie that are called transition metals. Now, the transition metals are potentially some of the most familiar metals. This includes iron. This includes, you guys probably have some familiarity with nickel, copper, silver, gold, zinc, cadmium, nickel and cadmium being used for your batteries. Mercury is a transition metal as well. There are others in here that people are not as familiar with typically. But yeah, iron, manganese, chromium, copper, silver, and gold, of course, being the other 3 big ones when compared with iron. They are transition metals. Okay, so we've talked about everything up to section 2.6 of this particular chapter. So let's actually take a step into the next section of this chapter, which would be section 2.6 of the topic electronic structures of atoms. And this is not a topic that you can technically cover in a tiny subsection of a single chapter. This topic, this little tiny subsection, this actually is hinting at topics taken from a much more high-level portion of chemistry that is known as quantum chemistry. Well, I should say we, since I've written this specific book, to my knowledge. But what this does is this takes a very qualitative approach to the information that we learned from looking at quantum chemistry. And so, of course, you can see from chapter 2, that section 2.6, the learning objective, they say, describe the distribution of electrons into shells, subshells, and orbitals around the nucleus of an atom. So that means that there is an organization to how electrons exist in that probability space around the nucleus. And that general organization they just listed, they gave you, it starts with shells, and then of course you have those, within those shells there are shells, and it's within those subshells that you actually find the orbitals. And those orbitals, of course, are actually where we could quote unquote say where the electrons reside. If you have been reading the book or paying attention to some of the material that we've gone through in the past, or at least some of the information I will be posting. I know the modules are not appearing in order at the moment, but earlier parts of chapter 1, especially when we talked about atomic theory, it mentions that electrons exist in orbitals. And now you can see that it's actually even, unfortunately, more complex than that. The orbitals actually exist in subshells, and those subshells exist within shells. So once we understand this layout and begin to understand how these relationships function, we can then actually understand the periodic table more effectively. Why does it have such a weird shape? Why do the numbers not necessarily coincide the way they ought to? So to begin with, of course, this is where we start to talk about a little bit of history, because some interesting things happened. So in the mid 18th century, you had a Russian by the name of Mendeleev. And he is one of the original people that came up with the predecessor to our current existing periodic table. There were a couple of things about his periodic table that didn't quite coincide with the one we have. I believe he organized it based on atomic weight, or by the atomic weight rather than by the atomic number. Our periodic table is organized by the atomic number rather than atomic weight. However, he did such a good job of predicting and understanding the way that atoms, and specifically, I should say, the elements are related, that his periodic table actually contained gaps that predicted unknown elements. He predicted the location of them on the periodic table. He predicted some properties about them. So that was Mendeleev. And then in the 1920s, skip a little bit of time, move forward to the 20th century. And it's in the 1920s that you start having people, including Einstein, who worked on some of this. But in the 1920s, specifically a gentleman by the name of Erwin Schrödinger, he came up with some of the fundamental assumptions, and more specifically, he came up with the equations that give rise to the orbitals, as well as the other pieces of information that then exist. So these equations, we should say, and subshells, and those shells, of course. So when I say quantum, this is directly related to, and we use the word quantum because we talk about energy and more specifically, electron behavior as being quantized. So the question, of course, is, well, then, what does the word quantized mean? And if you decided to flip back to the back of your book and look up in the index, unfortunately, you'll discover that the book doesn't give you a definition. And that, of course, is probably going to be very frustrating if you did it before I started to have this conversation with myself about this topic. However, if you are reading the chapter, even though you're not looking at the glossary, you'll see that the energies of the electrons are quantized. What that means is, and the definition is kind of hidden within the chapter, it means that quantized values, well, we can say that values that are quantized are values that are restricted to specific defined, basically finite is another word that kind of fits into this definition, values. It is not like your typical look at numbers. It is not a continuum, a continuous range of values. You know, if you measure temperature with a thermometer, the temperature changes smoothly and you don't see it stuck at like a stepwise function. So to compare this to what we normally think of when we're doing measurements, your standard unquantized values are continuous. And if you've drawn graphs, if you take an algebra, then you're familiar with the idea of the fact that your function needs to be continuous. However, you may have heard of a step function. And a step function basically looks like you have a certain value and then it'll jump immediately to another value. That line doesn't actually belong there. When I say a step function, it essentially should look more like you are moving along and within a particular region, it is stuck at one value and then it'll literally jump to another value. And there is no actual value for that function in between. And you can see that this would be quantized, limited to specific defined values. And so the values of the shells, the values of the subshells, and the values of the orbitals are limited to quantized values, hence the name of quantum chemistry, because we're talking about chemistry now that is defined upon this concept of limited specific values. Okay, so one of the things that was discovered when you look at an electron, when you look at electrons that are within orbitals, or in general, we should just say, when you're studying the atom and you're looking at electrons surrounding the nucleus of hydrogen. Hydrogen is the easiest one to study for this because there's just a single electron and there's just a single proton. Sorry, I managed to mute myself in this. There's a single proton within the structure of the atom. And so what happens is you can hit this, and this is the, of course, H atom. You can actually hit the H atom with, if you very, very narrow, essentially, if you can, you dial it down to a single wavelength of electromagnetic energy, which essentially we're talking about light, but the electromagnetic energy is more than just visible light or the ranges of light that are not visible to the human eye. All of that aside, basically what you do is you pick very narrow defined single wavelengths of electromagnetic energy, and you discover that only specific quantized values will be absorbed by the electron surrounding the nucleus. So you'll be shining light, essentially, of a very narrow, very defined wavelength. And only specific values will actually be absorbed by the electron. And what happens is, essentially, the theory is that within the H atom, so if this is the nucleus down here, which we'll call kind of ground zero, so here's the nucleus, and there's the base energy level, the lowest resting energy level of the electron, you will hit just the correct wavelength or frequency, whatever you want to call it, basically whichever value you choose to look at the electromagnetic energy. Because for electromagnetic energy, essentially E light is equal to, the most general thing is the frequency multiplied by Planck's constant. There's a couple of other equations in there that you're not responsible for, I believe, in this course. Let me double check that, of course, when I look back at my notes later. But there's a couple of things here. The speed of light is equal to wavelength times frequency, where this is equal to frequency of light and this symbol. So this is nu, and you got lambda, and this is the wavelength of light. And so, of course, we can either use this function, or another option is, of course, you can do some manipulation of the equation and come to the fact that wavelength, the speed of light over wavelength multiplied by Planck's constant is also equal to the energy of light. And so what I'm trying to show you here, of course, is that there are direct correlations between the wavelength or the frequency and the energy of the light that you're shining. And that's important because the ultimate thing that I'm trying to emphasize here is that when the energy of the light absorbed by the electron is equal to this energy gap, so the energy gap between energy levels within the atom, you get actual absorption. So when the electron is hit, not just absorbed, when the electron is, when energy of light hits the electron, and it is equal to the energy gap between these two energy levels, you get absorption. And only when the energy of the light is equal to the gap there in energy will you get absorption. The energy cannot be absorbed unless it is equal to the gap in the energy necessary to go from this lowest energy level to the next higher energy level. So this is one of those discoveries that was made with the hydrogen atom, and it was noticed that you would get this excitation. So when the energy of light equals the energy gap between levels in the atom, the energy of light is absorbed, and the electron rises, and this is in the H atom, to a higher energy level. This electron is now what we will call excited. So you can excite an electron in the hydrogen atom by hitting with a specific wavelength that will actually be absorbed, and that energy that is absorbed must be equal to the energy difference between the two levels. And therefore, this is how we know that electrons exist in quantized states, or very specific states within the atom based upon this observation. You can't just shine any old wavelength or any old frequency of light and get this transition between lower energy level and higher energy level. Not only that, but something else to keep in mind is that when you remove the energy of light that drove excitation, eventually the atom, the electron within that atom will relax and release its own energy of light equal to the original that it absorbed. So it'll release that energy of light back as it returns to the lower unexcited state. So we're talking about now this electron that has been hit by a photon, and we should define what that is too. We'll do that in a second. So this electron, a low energy level, absorbs a specific wavelength of light, gets kicked up to the higher energy level, and the difference in those two energy levels within the atom are equal to the energy of light that is absorbed by that electron. And then after a while, the electron will fall back to the lower energy level and release that energy back as the same equal amount of energy. Okay. Now, the book, I don't believe, let's see, glancing at the book, of course, does the book actually spend much time talking about light? And it does not actually, but I'm going to mention a couple of things about light because I believe you guys should have some of this knowledge. Now, light, and less specifically, electromagnetic radiation or electromagnetic energy, as the name implies, is both electronic and magnetic. So there you can already see a duality here. There's already a dual nature to electromagnetic energy, and it gets even more interesting. You can look up a gentleman by the name of de Broglie, how you pronounce it, if you were speaking the way he would want it pronounced, since he was a Frenchman. But some people might say de Broglie. Anyways, de Broglie, what he discovered was an equation that he derived an equation that relates mass to energy. And without actually giving the equation and going to the details of that, essentially what it means is that everything in existence has the following dual nature. And I'm not talking about magnetic and electric. That dual nature is, one of those natures is a particle nature, which essentially is to say a nature of mass or existence as some sort of particle or mass in the universe. And the other part of that nature is a wave nature. So de Broglie demonstrated, and clearly from his equation derived and then demonstrated, that everything has both a particle and wave duality, which is absolutely crazy to think about. This means that you can actually calculate the wavelength of a human being. You can calculate the wavelength of a planet. You can calculate the wavelength of an electron. Now, that is actually a lot easier to do and easier to measure than the wavelength of a human being, because the size of the particle and the size of the wavelength, if I were to show you the equation, you'd discover that the size of the particle is inversely related to size of the wavelength of that particular particle. And what that means is, therefore, the larger the particle, the tinier the wavelength. And to avoid continuously writing out wavelength, I will use the symbol most often used for wavelength that I briefly showed earlier in lecture. That's the Greek letter lambda. Lambda is used for wavelength. So that also means the smaller the particle, the larger the lambda or wavelength. Okay, I'm going to pause here for a second. Now, these topics that I'm mentioning, I know stray outside of the book, and I don't like doing that. It's I want the book to be as easy to follow, and I want my lectures to be as close to the book as possible. However, some topics need to be covered in order to give you guys a slightly larger picture of how these things were discovered. And in my opinion, some things help to understand better the complexity of this situation. The frustrating, especially for the first time you see these topics, how complex these things are. They are not simple, but it is made a little bit more simple, at least in my mind, when you look at the bigger picture. Okay, so now keep in mind wave-particle duality. What this means is everything, including light, has a wave-particle duality. Electrons have wave-particle duality. Humans have electron-particle duality. Everything in existence has wave-particle duality. Okay, and the name of the particle of light is a photon. So a photon is a quantized particle of light. And that is extremely, of course, interesting and important to mention. So now when I say, when the electron in that hydrogen atom we were just talking about We're just using the H atom as an example because it's such a simple atom. It is the most simple atom, and it's the easiest one to wrap your mind around. When the electron, in any atom, but we'll say the H atom for our example. Okay, just keep in mind this is just the example, the H atom. When the electron in the H atom absorbs a photon of specific wavelength, it gains the precise enough energy to jump up, be excited, to the next energy level. So photons are quantized, energy levels are quantized, okay? And therefore, you can see the direct connection, how these things, hopefully you can see how these things relate. So the photon gets absorbed. Now, when the electron in the higher now energy level, the term I think I used earlier, and we generally use, relaxes back to its lower resting energy level, it releases another photon of energy and wavelength and frequency. So frequency, energy, wavelength, energy, frequency equal to the one absorbed. And again, also equal to the transition back to the resting energy level. Okay, so quantization, specific values. Electrons exist in quantized energy levels within the atom. And the specific details of where those electrons exist are quantized. Those quantized values come from the Schrodinger equation, and this can be demonstrated by utilizing the fact that quantized packets of light called photons are required to observe the transitions between specific locations that the electron can exist. It can't exist anywhere in between those quantized states. Now, I'm not going to go into much more detail about this stuff. I just wanted to mention a few things to you that you may eventually see in the world around you or in other classes, if you haven't already. Some of you may actually be familiar with some of these concepts. You may have encountered these in physics courses or physical science courses you took, perhaps a previous chemistry course you may have taken. It may even be something you encountered in biology. All of that aside, what we're really talking about is the quantization of the location of the electron. And so what I really want to then go back to is there are what we call 4 principal quantum numbers associated with the identity of every electron within each atom. And I'm not going to bother giving you specific names. There are names associated with some of these rules. There is even a specific rule that says within an atom, so within a specific atom, every electron must have a set of 4 entirely unique quantum numbers. Okay, so within every atom, every electron has a unique identity, and those identities can be described by a unique set of quantum numbers, these 4 principal quantum numbers that I am mentioning at the moment in very general terms. Okay, there's a couple of other little notes about this. 3 of the 4 principal quantum numbers are directly originating from, are directly determined by the Schrodinger equation. And interestingly, and 1 is not. There's actually a quantum number that is not determined by the Schrodinger equation. The Schrodinger equation predicts 3, but fails to predict a 4th quantum number. Now, we are going to pause here again. And in fact, we're going to stop this lecture here before we proceed on to talking about these specific quantum numbers.